So our next speaker is Nancy Williams and colleagues. Nancy is a graduate student at Oregon State working on the SOCOM program, and I want to just mention that, man, there is a great group of graduate students and postdocs working in the SOCOM program, and Nancy's going to represent them.
Thanks, Ken. So as Ken said, I'm at OSU. I work with Lori Juranic, and I also work closely with Dick Feely and Ken, Lynn, and Jorge, and a lot of other SOCOM contributors, so thanks to all of those people. So I'm going to talk to you guys about the carbon observations we're making from these SOCOM floats. So just to do a little carbonate chemistry review, there are 4 measurable variables in the carbonate system. So we have total alkalinity, which we'll call TA, total dissolved inorganic carbon, or DIC, pH, and I'm going to use the total scale for the rest of this talk, and the partial pressure of carbon dioxide. And those 4 variables are all related by a set of equilibrium constants, and I'm not going to show you those equations because they're pretty ugly, honestly. But thankfully, there are a couple of programs that allow you to calculate the carbonate system. So as long as you have 2 of the carbonate system variables, along with temperature, salinity, and pressure, you can calculate the other 2. And you can also calculate other parameters like the saturation state of aragonite or the Ravel factor. So usually when you want to measure the carbonate system, we go out on a ship and we get bottle observations or underway measurements, and we'll measure at least 2 of the variables, and sometimes even 3 or 4. But on the floats, we are only getting pH. So how do we get from measurements of pH to the rest of the carbonate system? So there are 2 ways that you could do this. Since we have a pH sensor, we can combine those measurements with an estimate for alkalinity. And there are a couple of, actually there are a lot of methods out there for that. The most recent one to come out is called LIAR, which stands for Locally Interpolated Alkalinity Regression. And I thought that was a pretty clever name, kind of to remind you that it's an estimate and not necessarily the truth. And then I also developed a regional algorithm for just the Southern Ocean. And those are based on temperature, salinity, pressure, and oxygen, and also a proxy for location. So if you combine those 2, then you can calculate PCO2, for example. If you didn't have a pH sensor, or say you don't believe your pH data, then you could actually directly estimate pH using an algorithm like this. And so you're basically fitting pH as a function of salinity, temperature, pressure, and either nitrate or oxygen. And you can read about that in Juranic et al. 2009, 2011, or in my 2016 paper. So both of these have their pros and cons. So from the float pH, you really need high quality data. So it's got to be quality controlled, and having a quality controlled sensor relies on having high quality bottle data. The algorithms also depend on having high quality bottle data. They're independent of a pH sensor, but they're not perfect. So at the surface where oxygen and carbon decouple because their timescales of gas exchange with the atmosphere are different, then the algorithm isn't going to work that well. So this is sort of could get you in the ballpark, but it may not be, it's not going to be as good as a quality controlled sensor. And also these MLR algorithms can't account for anthropogenic changes because they're trained using data from a certain time point. So I'm going to talk mostly about how we quality control the sensor data. And to do that, we actually use an algorithm. So this algorithm is specially trained using just deep data, so data between 1,000 and 2,100 meters from 2 cruises in the South Pacific. So this is P16 2014 and S4P 2011. And those are direct bottle measurements of pH. So we're not using any pH calculated from other parameters. And so the RMS error of that algorithm is 0.004. what we do is we take the float, the raw sensor data from the float, and we calculate what we think the pH is based on the float temperature, salinity, and pressure, and oxygen. And if we look at the difference between the float and the algorithm at 1,500 meters over time, so this is looking at station 1 would be the first station, and then one station every 10 days. The deployments from this field season, 2015-2016, show very small offsets from the algorithm and essentially no drift rate. And this is sort of we learned through trial and error that the sensors need to be equilibrated with flowing natural seawater for a couple of weeks prior to being installed on the float and deployed. And as long as you do that, you get good results. So these are not going to require, they may require an initial adjustment, but then we'll continue to monitor them, but they might not need much adjustment later. And this is in contrast to some floats that were deployed in early 2014, the first floats. They had much larger offsets from the algorithm, and they also had some drift. So this is, they took almost up to a year to stabilize out. So we're really using the MLRs heavily to quality control these sensors. And just to plot those two together, the black lines are the 2015-2016 deployments, and the red lines are the 2014 deployments. So we're doing a much better job with the new equilibration method. And just to show you a little bit about how we do the quality control, we're calculating, like I said, we calculate what we think pH would be at 1,500 meters using the float data. So the blue line, this is the first profile. So the blue line is the raw pH from the sensor. The black dots are the bottle data. So that's the calibration data that's used to train the MLR. And so we look at the difference between the raw sensor and what we think pH should be. And we adjust the reference potential for the sensor to match the raw data to this algorithm estimate. And then we apply the reference potential to the entire profile. And so the black line is now our quality controlled float data. And just as a check to make sure that this process works at the surface as well, do the data match the bottle data, and they do within reason. We wouldn't expect them to match exactly because the first profile is actually not for about 18 hours after the calibration CTD cast, because that's how long it takes the float to go down and then do its profile on ascent. And I stole this slide from Ken. He's probably going to say it too, but this is basically what they do with the salinity sensors on Argo floats. So just a reminder. Okay, so now hopefully I've convinced you that you should believe this pH data. I'm going to talk a little bit about what the uncertainty is in using that sensor data with alkalinity to calculate something like PCO2. So the sources of uncertainty for this come from three basic categories. So the pH, the alkalinity, and then there's also some uncertainty associated with the calculation itself. So uncertainty in those equilibrium constants that relate all of the carbonate system parameters. So the precision of the sensor is about 0.003, and that's based on how stable the measurement is as the sensor profiles through a well-mixed surface layer where temperature and salinity are constant. And the quality control process itself introduces some uncertainty because there's uncertainty in the MLR algorithm. There's also some uncertainty in the pH measurements themselves because we bring the bottle to the surface, we measure pH at lab temperature and pressure, and then we have to calculate the in situ pH to compare with the sensor. So that has some uncertainty. So if we combine those, we come out with 0.007. And then, as I said, the alkalinities we're using are not exact measurements. They're estimates. And the uncertainty in those is about 5 or 6 micromoles per kilogram. And that uncertainty may be larger in the winter. We're working on quantifying that. But as I'm going to show you, the alkalinity is actually not that important for this calculation. So in this figure, I've plotted pH versus alkalinity and the calculated PCO2 at a given temperature, salinity, and pressure. And these lines are, more horizontal than they are vertical. So at a given pH, the PCO2 really depends mostly on at these conditions, the PCO2 depends mostly on the pH and less on the alkalinity. So Dixon and Riley, 1978, calculated that a 1% uncertainty in alkalinity converts to a 1% uncertainty in a calculated PCO2. And here we're talking about 5 micromoles per kilogram is about 0.2% uncertainty in alkalinity. So that's just 1 microatmosphere. So even if we're off in the winter by 3 times that, we're talking about 3 microatmospheres. So, and then I said there's also some uncertainty in these equilibrium constants. So if we combine all 3 of these sources, the total relative uncertainty in a PCO2 calculated from the floats is about 2.5%. So that's at 400 microatmospheres, that's about 10 microatmospheres. And to put that in perspective, the uncertainty from a ship-based underway PCO2 measurement, which is what's used in most of the presentations that we saw this morning, that uncertainty is about 1%. So we are looking at something that's larger than that, but I'm going to argue that we're still learning something from these floats. And no matter how good we make these pH sensors, there's always going to be a 1.43% uncertainty just because of the calculation. So that's something to strive for, I guess. And a final check on is this uncertainty sort of a realistic estimation? I compared the float PCO2 calculated from the first profile with the underway PCO2 measured on board the ship. So we were lucky to have that for 2 of our big deployment cruises. And the standard deviation of the difference is about 3.5%. So that's a little bit larger than 2.5%, but as I said, there's a time difference, so that could lead to some increased difference. So I think this uncertainty estimate is reasonable. And so now this is, I'm showing some float data now. This is float 9031, which is down here in the South Pacific, north of the ACC. And I'm comparing the float data in black with shaded error bars for the 2.5%, with 2 climatologies, the Takahashi 2014 climatology and the Landschutzer 2014 climatology. And this is delta PCO2. So negative means the ocean is going to absorb carbon. Positive means the ocean is going to outgas. So from deployment in 2014 until now, the float matches the climatologies quite well. However, for this float, which is float 9099 down here in the seasonal sea ice zone, we're seeing some pretty big differences, and that is especially in the winter. And why might that be? Well, I'm showing here all the SOCAT data from the database in the Southern Ocean for all time. So this is, the color is the month. But if you take just winter data, which is June, July, August, and now this is colored by year, we see that there really isn't very much data. So even though we have a large uncertainty on our estimate, I think we're still going to be learning something from the floats. And a little bit of a change of gears. We're going to use the pH to calculate the saturation state of aragonite, and that is important for shell-forming organisms. So if omega is greater than 1, then the calcium carbonate is stable, and if omega is less than 1, then dissolution is favorable. So just some preliminary results here. This is omega at the surface. Something's cut off, but it's 1.1, 1.2, 1.3. So what we're seeing is that the seasonal cycle in omega north of the ice is much smaller than, say, for example, this red float, which is experiencing seasonal sea ice cover. So when the ice opens up, there's a big bloom, omega goes up, and then in the winter, respiration takes over and omega drops. So we're getting seasonal cycles, we're getting interannual variability even. And why do we care about the seasonal cycle in omega? Well, this is a paper, Sassi et al., 2015, used the seasonal cycle in omega at this station at 60 South in the Pacific, or I think they just picked a location. And they projected forward in time using the business as usual emissions. So omega is going to drop generally as the ocean absorbs carbon dioxide. And they're looking for when do we see undersaturation at that station. So if you use the mean omega, you would calculate that undersaturation is going to happen around 2070. But if you have a seasonal cycle in your omega, then you see your first undersaturation much earlier, and it's not until about 20 years later that the water is undersaturated year-round. So, and studies have shown that the duration of exposure to undersaturated waters is important. So knowing the seasonal cycle is going to be important for these kinds of projections. And so just to sum up, the pH sensors conditioned in natural flowing seawater are stable, and the unconditioned sensors are being quality controlled using the MLR algorithm. And our float-based PCO2 estimates have an uncertainty of about 2.5%, and this does not depend heavily on your alkalinity estimate. And we're observing seasonal cycle and interannual variability in omega, I think it's safe to say, for the first time on floats, both with and without pH sensors. I didn't cover that, but there's an algorithm for omega and it actually matches the omega calculated from the float quite well. So that'll all be hopefully coming out in the next couple of months. But that's it. Thank you.
Time for a few questions for Nancy. Last chance, going once. Okay. If not, then thank you very much, Nancy. And